In 1938, Stanley Hooker arrived at Rolls-Royce in Derby with an awkward confession. He was barely an engineer in the workshop sense. What he did have was mathematics, physics, and a grip on airflow that the Merlin badly needed. While the factory hammered around him, Hooker retreated to calculations. He treated the engine's supercharger as a problem in moving dense air, then sketched a two-stage answer that could feed the cylinders high above the battlefield. On its first trial, Hooker's solution behaved exactly as the sums said it should. The gain was brutal, about 113 kilometers per hour in speed and roughly 3,000 meters of extra fighting height. For the Spitfire, that changed the argument with the Focke-Wulf 190. British pilots could climb higher and fight on better terms. Hooker then pushed beyond pistons, backing Frank Whittle's jet turbine work and helping Rolls-Royce into a new kind of power. Soon after the war, that path was tied to a world speed record. Again and again, Hooker was called toward engines that were in trouble or at the edge of what aircraft could do. The Britannia needed saving. The Olympus would drive the Vulcan bomber and later Concorde. Across that arc, his instinct linked the wartime Spitfire to the age of supersonic travel. This film follows the unlikely engineer whose engines powered some of the fastest and most advanced aircraft of their day. Looking back 40 years later, Hooker did not choose the jets or Concorde as his proudest moment. He pointed to the two-stage Merlin supercharger. In his telling, he proposed it, specified it, ran the calculations and watched it work first time. The reward was the same stark figure he never forgot, about 113 kilometers per hour on the Spitfire's speed and around 3,000 meters on its combat ceiling. Test pilot Marshall later described climbing past a Focke-Wulf 190 with the German pilot unable to follow. For Hooker, that first real aviation contribution remained the decisive one. Hooker's work mattered because the Merlin was being asked to breathe where thin air starved engines of power. His supercharger technology forced more air through the system, and the engine's output rose from an early war level to about 2,000 horsepower by the war's end. That gain helped the Royal Air Force stay ahead of German fighters. One contemporary assessment went further, arguing that without this work, the Royal Air Force might not have prevailed in the Battle of Britain. Hooker had not set out to be an engineer. The son of a Kent farm manager, he had built a life around physics and mathematics. By 28, after Imperial College, Oxford, and a post at the Admiralty, Rolls-Royce pulled him into aircraft engines. Rearmament was filling new factories with production jobs, and Ernest Hives needed bright theorists at Derby. Hooker remembered the interview as a cold, damp January day in 1938. He walked through Derby wondering why he had come at all. The Admiralty had given him a comfortable research job, and he had not even warned them that Rolls-Royce was courting him. In Hives' office, his papers were spread across the desk in front of him. Years later, Hooker could still point to that very desk as the place where the turn began. Hives studied the file, a London mathematics degree, an Oxford doctorate, and a stack of theoretical papers on aerodynamics. Then he cut straight to the weakness. Hooker admitted he was not much of a practical engineer. Hives treated that as fixable. Rolls-Royce could teach the workshop craft. The awkward part came next. Hives asked who employed him, then rang Sir Charles Wright at the Admiralty before Hooker had told his own bosses anything. After the call, Hives reported that the Admiralty had just promoted him, but Rolls-Royce could still take him if it chose. When Hooker finally arrived, Rolls-Royce was a storm of telephones, typewriters, drawing boards, and urgent calculations. Then someone put him in a small glass-partitioned office with a desk, a bookcase, a telephone, and a chair. That was all. For 2 days he had almost nothing to do. On the third, he brought in the Times, lit his pipe outside the permitted smoking hour, and waited for someone to object. When boredom finally beat him, he walked next door. There, younger men were buried in drawings and sums. In the corner sat a quiet, grey-haired older man, so still after lunch that Hooker suspected he was asleep. At Derby, a stack of supercharger test curves landed on Stanley Hooker's desk almost by accident. He had asked a test engineer what his rig actually did: drive a supercharger with an electric motor, then record pressure, airflow, and the rest. To Hooker, that raw data was gold. He knew air, pressure, and temperature, even though he had not yet worked close up on an aero engine supercharger. From the curbs, he teased out compressor losses, diffuser efficiency, and rotor efficiency, then wrote up the changes he thought the compressor needed. The report went to the chief engineer, who found it interesting enough to pass upstairs to the head of experimental engineering. A week later, that quiet report came roaring back. Hooker was about to leave at 5 o'clock when the experimental chief burst into his office, waving the paper and asking if he had written it. Hooker said he had. The reply was blunt. He was now responsible for superchargers. That was his first real job. Then war was declared, and the next Monday brought Hive's usual technical review of the Merlin. He came in, sat down, and made the point plain. Britain had to win, not come a respectable second. He then went straight into the agenda. Rolls-Royce, already prepared by Hives, could double output almost overnight. The men would pay for it in hours and exhaustion, but the machines, materials, and tooling were waiting. When the war began, Derby became the single source for the Merlin engines that would fight in the Battle of Britain. At the start, men were working 18 hours a day, 7 days a week. There was no second Merlin factory in the country then. By 1940, the pressure inside the works was ferocious. The Hurricane and Spitfire carried Rolls-Royce engines smaller than the German engines they faced, so Derby had to squeeze equal or greater power from less capacity. That meant relentless development. Across the war, that pressure pushed the Merlin from roughly 1,000 horsepower to 2,000 without a basic redesign. The same family of engines still went into Lancasters, Hurricanes, Spitfires and Mosquitoes. That mattered. Rolls-Royce kept refining what it already had, while the Germans took a different road with the Focke-Wulf 190 and its big air-cooled engine. Hooker called that approach brute force and bloody ignorance at the time. Inside Derby, the obsession was simple enough: keep the Merlin ahead of the Germans. By the summer of 1940, piston-engined fighters were fighting overhead in the Battle of Britain, but on the ground, in a disused foundry, a secret machine was being nursed into life: Frank Whittle's jet engine. The idea still had few champions. Stanley Hooker was one of them. He kept pressing Hives to go and see it. Hives asked what the engine actually did. Hooker answered in terms of thrust, about 1,000 pounds. To Hives, that sounded absurdly small. What use was such a pull? The argument did not end there. On a Sunday, Hives took Hooker to see Whittle's engine running. Whittle explained the advantages while Hives walked around saying little. Then Hives noticed the real weakness. There were hardly any engines in the place. Whittle had only 2 because he could not get enough parts made. That changed the conversation. Hives told him to send the drawings to Rolls-Royce, and Rolls-Royce would make the bits. They did. The Ministry of Aircraft Production had already put Rover on the early Whittle engines. By 1942, Rover's management and Whittle were barely speaking. Hooker heard about the quarrel and told Hives. Hives wanted the jet, and he saw his chance over dinner with Rover's chairman. The meal was modest, 5 shillings a head, but the bargain was anything but small. Hives asked why a car company was struggling with an aircraft engine. Then he offered a trade: Rolls-Royce's tank engine factory at Nottingham for Rover's jet engine work. Rover accepted. That swap gave Rolls-Royce Barnoldswick and responsibility for developing and producing jet engines. The team was young. Even Stanley Hooker, its boss, was only about 35 or 36. The speaker himself was 30. They also had a rare freedom to alter the engines fast. If a new construction idea did not demand too much manufacturing, tests could be run overnight and examined the next day. When parts were needed, Rolls-Royce could call up castings, sheet metal work, and the rest. Advanced changes could move from idea to test in weeks. In 1944, the Meteor answered the doubters by catching a flying bomb. Hooker and his team had shown that jet power could be more than a laboratory promise. The ministry then asked for an engine giving about 18 kilonewtons of thrust, roughly twice the previous mark. Around then, Hooker was sent to America, where cooperation with the Americans was unusually open. They had been told what Rolls-Royce was doing, and they even had a Whittle engine. But at General Electric Company, Hooker found an engine already running close to 18 kilonewtons. He came home and pushed the target to about 22 kilonewtons. A call to George Watt at the ministry was enough. In those days, Hooker remembered, a decision like that could be settled almost on the spot. That pace carried straight into 1945. Work began in January. By mid-year, the engine was running, and in October it helped take the world speed record. The record run pushed an aircraft beyond about 960 kilometers an hour. For Hooker, the lesson was bigger than fighter performance. The new engine type was beginning to look like the future of air transport as well. The advance was rapid, and Hooker was among the first in this story to see how wide the change might reach. Derby had lived with speed for nearly 20 years, with Rolls-Royce workshops turning out record-breaking engines. There, the Derwent jet engines were being made, machines built to drive an aircraft into the region where smooth airflow tears into shockwaves. Those shockwaves had a human echo. One of Hooker's engine projects, the Avon, ran into trouble, and the dispute with Hives turned sharp. Hives believed too much depended on that engine to leave it at Barnoldswick. To him, Rolls-Royce meant Derby, not the improvised works he dismissed as a garage. The engine would go back there. Hooker asked where that left him, and Hives's answer was brutal enough. He was to go home for 3 months. For a man who had built the turbine team, it landed hard. Hooker took it as a bitter repayment for 11 years under Hives. The exchange did not cool down. Hives pressed him for an address. Hooker refused to give one. If the company wanted him, he said in effect, it would have to find him through his bank. Then he drew the line that mattered. If Hives sent him home, Hooker would never again work in a factory under Hives's control. They parted at Barnoldswick. Looking back, Hooker remembered the day as miserable and traumatic. The break was startling because Hooker's Barnoldswick turbine group had delivered so much. To people around Rolls-Royce, he stood just behind Whittle among Britain's gas turbine engineers, and some thought the comparison reached even further. Then the troubled engine was pulled back to Derby. What followed felt almost like a demotion. Hives brought Hooker back, but the post was modest, head of the Derby research team. For colleagues watching, it was a shock. That job fell far short of what Hooker believed he had earned. Hives, he later said, had promised him the chief engineer's chair at Rolls-Royce. By then, Hooker was about 40. In his own reckoning, that was not early career. At about 30, he had been running the turbine work. At 40, he felt ready for the whole firm. The promise and the posting no longer matched, so Hooker walked away. Bristol Aeroplane Company was moving into jet production, and it needed the experience Rolls-Royce had just sidelined. The pressure was immediate. Bristol's new passenger aircraft, the Britannia, was caught in serious engine design trouble, and failure could threaten the company itself. Hooker's first task was to rework the troublesome turboprop engine. He felt the weight of it because, as he saw it, he was the only man there with real jet engine experience. That was a lonely position. At Bristol's engine school, Dr. Stanley Hooker now spoke as chief engineer to flight crews from the Royal Air Force, the Royal Canadian Air Force, and Canadian Pacific Airlines. The lesson was power, more of it, drawn from the turbine engine. He showed them opened casings and the inner components that made the power. Those were heady years for Bristol, with government money flowing into new fighter and bomber projects. When the Vulcan, the Flying Dart, needed an engine, Hooker wanted Bristol to beat what his old Rolls-Royce colleagues could build. The old grievance now had a test bench. In 1958, the Olympus was a bragging point with a punchline. Hooker was proud of it, and in his telling, it was the most powerful engine in the world at the time. He sent a Christmas card pairing Mount Olympus, just under 3,000 meters high, with the Olympus engine, delivering about 43 kilonewtons of thrust. One Rolls-Royce friend replied with the perfect engineer's jab, asking how the weights compared. Then the engine became the heart of TSR-2, ordered as the costliest aircraft project yet, and described as a strike and reconnaissance machine. The Air Ministry kept changing the brief. Arguments dragged on, the timetable slipped, and the bill climbed into dangerous territory. Hooker later remembered challenging a senior air staff officer over the demanded operating radius for TSR-2, about 1,600 kilometers. To him, the number felt plucked from the air. The officer treated it as an objective. Hooker did the arithmetic in his head and warned that the final stretch, roughly 240 kilometers, could burn money at about £620,000 per kilometer. Looking back, even that sounded too low. Within a few years, TSR-2 had flown, and those close to it saw an aircraft of dazzling performance. Then, in 1965, it was killed almost overnight. Hooker blamed the lurching policy behind it. A late 1950s defense paper had argued that piloted aircraft were finished and missiles would take over. Then the missile answer vanished too, after the Americans cancelled the program Hooker remembered as Blue Streak. The result was absurd. No missile, and no manned aircraft either. A new minister came in and ordered aircraft again, including a supersonic vertical takeoff design and TSR-2. Then Dennis Healy arrived, judged the program unaffordable, and turned instead to buying F-111 aircraft on credit. So the policy swung in, and out again. Hooker saw less strategy than a boat race. His best remaining hope for the Olympus now shifted to the supersonic airliner Concorde, but that too became a long siege. 18 years of development, with cancellation always in the air, before its first scheduled service in 1976. Through the fights over TSR-2 and then Concorde, Hooker had also been nursing another remarkable idea: the Pegasus engine for a vertical takeoff fighter, the jump jet that would become the Harrier. At first, there was no aircraft ready to take it. Hooker admitted he had not pushed hard, partly because he was not fully convinced by the concept, and partly because TSR-2 was swallowing attention. Then a letter arrived from Sidney Cam at Hooker, asking what Hooker was doing about vertical takeoff. Cam was the company's great fighter designer, linked in the transcript with names such as the Heart, Fury, Demon, Hunter, and Hurricane. Hooker sent in the Pegasus brochure and, for a while, thought no more about it. Weeks later, the telephone rang. It was Cam, sounding as irritable as Hooker remembered him. He wanted to know when Hooker was coming to see him. Hooker asked what the subject was, and Cam said he had an aeroplane wrapped around Hooker's vertical takeoff engine. Hooker went up to Hooker. There he saw the drawing, a prototype that already looked very much like the Harrier, with the Pegasus engine sitting inside it. A casual brochure had turned into an aircraft. Hooker assumed Hooker would start gently, with ordinary forward flight. After all, by pointing the nozzles backwards, the machine could fly like a conventional aeroplane. He suggested proving that first. Cam would have none of it. Hawker aeroplanes, he insisted, were always good aeroplanes. So they went straight for vertical flight. The aircraft was tethered like something on a line, and when it lifted, it slewed about wildly. The idea worked, but only just. At the start, it was brutally hard to control. The Harrier went on to become an international success. Hooker had backed it early, and he kept backing it. His stubborn faith helped keep the project alive. In the Falklands War, the Harrier finally faced the test that mattered. Around the world, from Derby to America and beyond, fortunes had been poured into vertical takeoff and landing fighters. None had matched it. The jump jet still stood as the answer others could not quite copy. By then, Stanley Hooker had long since retired. Yet without Hooker, there would have been no Pegasus engine, no Harrier, and in this telling, no task force victory. Hooker had stepped away in 1967, retreating to his country house near Bristol. Rolls-Royce, his old employer, had absorbed the Bristol firm and become one of the main supports of British aircraft engineering. Then, in 1971, the impossible happened. Rolls-Royce ran out of money. Edward Heath's government acted fast, taking the company into public ownership, but leaving aside the RB211 engine at the heart of the disaster. That is why Stanley Hooker was summoned back. He was the man who could persuade the government that the RB211s still deserved a future. Inside the engineering teams, morale had collapsed. People were blaming one another, arguing over who should go, while the strongest people were not always on the engine itself. Hooker saw that as a disaster. His first task was blunt: get more people and better people onto the job. Once again, he was at the helm, with the fate of the RB211 program resting on the result. Hooker did not come back alone. He drew in trusted colleagues from earlier days, among them Harry Pearson. The effect was immediate. Witnesses remembered him giving the engineers their nerve back without wasting energy on blame. The RB211, they said, had the makings of a good engine. Hooker forced the work into shape and made it a fine one. Had it failed completely, British high-technology engineering would have taken a grave blow. Instead, he gripped the engine and the people building it. For him, the motive was simple: build a strong engine, a reliable engine, one that did its job and did not kill anyone. Most engineers, he believed, gave their lives to that kind of work. But the world Hooker had known was slipping away. In his early career, the engineer's judgment carried the day. By the time he retired in 1978, the accountants had taken the commanding chair. The old approach began with the machine itself. What must the engine do? How long to draw it? Build the first experimental examples, test them and move toward production. Only then came the cost. Now, Hooker thought, the order had flipped. The first question became the price. Then came production timing, the number of development engines and the length of the design work. Whether the thing was actually any good seemed to arrive last. One colleague reached for Einstein as the measure of genius, then placed Hooker just below that line. Very clever and a very good engineer. People like that, he said, do not appear often. You may get only a few in a generation or in a country. The story now turns back to 1938 as war clouds gathered over Europe. The Rolls-Royce factory at Derby took on a new weight. It had been the company's home since its beginning, and from there came one of the great British contributions to victory. A hand-picked group of designers, engineers and executives brought it forward under the company's senior leadership. The company worked in the tradition associated with Sir Henry Royce. Nothing short of perfection would do. Managers and workers pressed on with the development of an aero engine meant to give democratic air forces the power to defeat the enemy in the skies and strike his industries. That engine was the Merlin. Away from the immediate danger of air attack, a quiet country house deep in the Derbyshire countryside housed the Rolls-Royce Aero Planning Department. There, under intense secrecy, designers refined the Merlin using knowledge gathered from earlier engines. At Derby, the Merlin's new shape existed first as figures on paper. The committee had settled the broad engine characteristics. Now the hard work began. Engineers fixed the main dimensions, drew plans for mass production, and built wooden scale models of engines and power plants. Those models were not toys. They exposed frontal area, weight, undercarriage movement, and the centre of gravity before metal was cut. Then the draftsman took over, producing thousands of working drawings for the prototype. Those drawings had to reach the shops, so Derby created a blueprint department, turning out about 6,000 copies a day. In the experimental shop, the prized tool was the man using it. Each job was different. The workers had to be versatile, among the finest in the Rolls-Royce organisation. The first parts soon appeared. Because this was one-off work, the machinery was less specialised than on a production line. When identical pieces were needed, such as connecting rods, a Keller copying machine did the repeating. On the Keller machine, cutters followed a master template and shaped several matching parts in one pass. But at this stage, there were few jigs or fixtures. A machined face had to be checked on the marking off table. Nor did a new engine usually begin as a complete unit. A future engine might have 12 or 24 cylinders, yet the first trial could be only one crankshaft section. From a single-cylinder rig, the first solid evidence arrived. Those single-cylinder results let the designers predict how the full prototype should behave. Once assembled, the engine went straight to the test house. There it was coupled to a dynamometer, a water brake that swallowed the engine's full output. By changing the load and speed, testers could measure its character. The panel watched everything that mattered: fuel consumption, boost pressure, oil pressure, coolant temperature, revolutions, power output, and more. From its first development, the Merlin's rated horsepower kept climbing. Later versions gave 2 or even 3 times the output of the original prototype, without major changes to the principal dimensions. After a test run, the prototype was stripped. Every part faced close inspection. If a component showed too much stress or wear, the chief engineer and designers decided whether the answer lay in design, manufacture, or materials. After the first testbed trials, the engine was tested again with the air screw fitted. Only then came the flight test. The Merlin was installed in an aircraft fuselage, and a Rolls-Royce test pilot took it into the air to prove the designer's calculations in practice. The Air Ministry had already seen the next problem. Britain would need quantity as well as quality. Rolls-Royce was asked to build a major Merlin factory away from Derby. Work began at Crewe in 1938. Then, in 1939, with war treated as certain, the company was asked for another plant, about twice Crewe's size. Glasgow was chosen, and work there began in July 1939. By early December, the first machine tools there were already cutting Merlin parts. Factory planning had been worked out before the floors filled with equipment. Engineers made scale silhouettes of every machine and even the workshop furniture, then moved them around on a floor plan until the flow made sense. The chosen layout was photographed, and copies went to the plant engineers. Once the machines were installed, Merlin production began at full scale. Mass-producing the Merlin while preserving Rolls-Royce precision brought problems on every side. Wartime blackouts slowed the factories. Military demands on road and rail made raw materials harder to move. Labour was just as serious. Training centres were opened across the country where Rolls-Royce craftsmen taught men and women to run specialised machine tools in purpose-built factory sections. To widen the supply of engineering draftsmen, the company also experimented with training women who had the right educational background. At Glasgow alone, more than 1,500 houses went up within sight of the works. Crewe had its own estates too, because the engine programme needed more than trained hands. It needed people moved, lodged, and kept close to the job. Women who had come through the firm's training proved they could handle demanding technical work, and many moved on into works drawing offices. Then transport had to catch up. Local operators helped run 126 special bus services using a depot inside the works so workers could ride straight out to the surrounding districts. Once those factories filled with people, they had to be defended as well as supplied. Volunteer workers formed Home Guard and Civil Defence detachments against attack from the air or the ground. Worker-manned fire brigades trained fast, with motor pumps and modern firefighting gear ready on site. Rolls-Royce may even have stood apart in one dangerous respect: its own bomb disposal unit, prepared to step in when an emergency turned deadly. The same scale demanded a medical system inside the works. Every new worker received a medical examination and an eyesight test. Each plant had surgeries and restrooms staffed by resident doctors and nurses. And to keep production from becoming a fight between office and shop floor, each factory set up joint production committees, bringing management representatives together with worker representatives and shop stewards. Behind the labour force sat another discipline: traceability. Huge reserves of raw material were built up, but nothing simply disappeared into the machines. A sample from every incoming bar, tube, rod or forging went to the laboratories for analysis. Each batch carried a number through every stage, with samples kept so a later fault could be traced back to the material itself. Some of the most valuable materials were light metals and other alloys developed in the Derby research laboratories, including the casting alloy known as Rolls-Royce 50. Those laboratories supplied the Allied war effort with much more than one famous metal. In the Rolls-Royce drop forge shop, alloy steel forgings were hammered out around the clock. The Merlin engine's most heavily stressed parts came from this work because forging could deliver accurately shaped pieces in high numbers. Under the blows, the metal's internal flow made it more uniform and better able to take strain. Then the story moved to Glasgow, where the light alloy foundry was unique within Rolls-Royce and perhaps beyond it. That Glasgow foundry spread across 2 full factory blocks, with core making, moulding and fettling arranged on the same flow production logic as the rest of the plant. Its layout was a major exercise in technical planning. Every kind of casting needed for Merlin engines was produced there. The material problems were many, which made the result sharper still. Much of the work was being done by trainees, and a large share of them were women. Core making showed how far the system had been broken down into learnable tasks. Work that once demanded long experience could now be done quickly and reliably by trainees of both sexes. The lighter cores were made by hand, mainly by women, at tables fed with ready-mixed sand from overhead conveyors. Each Merlin engine needed more than 300 intricate cores, yet the organisation made each separate job manageable. The heavier cores were made by men on machines. Several went into the upper half of the crankcase mould, where they formed the bearing webs. This was one of 2 main moulding bays set on either side of the furnace line. Most machines were roll-over jolt types, worked by hydraulic or pneumatic power and kept simple to control. The mould for the upper crankcase half was the largest on the Merlin engine. With its cores and moulding box, it weighed a ton. Yet size was not the same as complexity. Other engine castings were more intricate. Nearby, gas-heated tilting furnaces melted the aluminium alloy, chiefly Rolls-Royce 50, beside the mould conveyors. 2 sides at once, that is how the biggest moulds are filled. Pouring from both ends keeps the ladles within a size men can handle and helps the metal settle at a more even heat through the mould. To make sure the casting stays sound, the shop feeds it with large risers, often a great many of them. Then comes fettling, the hard clean-up work done with power saws and pneumatic hand tools. First, the runners and risers are cut away. On heavy castings, that surplus metal is massive. A twin handheld circular saw bites in from both sides, leaving the waste ready to snap off at the end of the cut. Pneumatic chisels finish the job, stripping flash and unwanted webs. No casting moves on until inspectors have looked it over. Before machining, the load goes through a heat treatment furnace about 27 metres long. The castings ride in on bogies pushed through the front end. Each incoming load drives a finished heat-treated load out at the far end. Inside, 3 heat zones are held by automatic controls, with temperature kept within plus or minus 2 degrees Celsius. Many Merlin castings are made another way, by die casting. Here, reusable metal dies replace sand moulds, cutting time because the same form can be used again and again. The die castings leave on a conveyor and go for heat treatment just like sand mould castings. Die casting lets the shop work to finer limits than ordinary sand casting. The surface comes out cleaner, and because the mould does not involve gases, the metal is usually more uniform inside. From there, the castings pass to the machine shops for finishing. Over recent decades, machine tools had grown into remarkably intricate automatic and semi-automatic systems. In the hands of trainees or operators classed as unskilled, they could turn out complex parts in huge numbers and still hold very fine accuracy. The label can be misleading. Many of those men and women became highly capable at one machine or operation. The old term remained only to distinguish them from the fully skilled Rolls-Royce operator. At the Derby works, those fully skilled operators had served long apprenticeships and absorbed the Rolls-Royce way of working. Their job was not merely to run a machine. They set it up, made the fine adjustments, and kept it producing accurate work while trainees handled the controls. Many of the machines themselves had been developed by Rolls-Royce engineers. That was the clever part. A component that would demand stacks of difficult drawings if made by hand could be produced on company-built equipment by comparatively new operators without letting the Rolls-Royce standard of precision slip. The crankshaft carries some of the fiercest loads in an aero engine. Making the Merlin crankshaft took more than 140 separate machining operations. To do that work, Rolls-Royce developed a whole family of special-purpose machines: vertical and horizontal automatic lathes, deep drilling machines, grinders, and lapping machines for the crankshafts themselves. The starting forging was heavy, about 113 kilograms. By the time machining was finished, the shaft weighed about 49 kilograms. The connecting rod was another part asked to live under severe stress. A fully articulated pair needed more than 160 operations before it was complete. At Rolls-Royce, inspection was not saved for the end. After every machining step, each component was checked before it moved forward. Women proved especially good at this demanding inspection work. And because a Merlin engine contained more than 11,000 parts, a large share of the smaller pieces came from bar stock on automatic and capstan lathes. Once the tools were set, much of this work repeated the same operation again. But a good operator still needed judgment and touch. The output reached by trainee men and women, many with no earlier engineering experience, was a serious achievement, especially on close limit work held to Rolls-Royce standards. Gears raised the bar again. The Merlin used about 90 different types and sizes of gear wheels, and every one had to be made with exceptional accuracy. For smooth running, the tooth form had to be right, and the metal structure had to be right as well. For helical gears, the works used a special gear analyzer. It drew an enlarged trace of the tooth profile, showing even small departures from the theoretical shape. The same care went into valves and valve springs, machined from forgings. Early valve forming work was done on turret lathes and automatic machines. Then the heads and seating faces received a protective layer of heat-resisting nickel-chrome alloy, applied in the flame of an oxyacetylene blow lamp. In the Merlin, even an exhaust valve hid a trick, a hollow stem half filled with sodium. Once the engine was running, that sodium melted at low temperature and sloshed through the stem, carrying heat away from the valve head. The springs behind those valves came off a purpose-built machine that coiled high-tensile steel wire continuously, then cut each spring to length. After grinding and finishing, the coils went into a tempering furnace, so a small part could survive the punishment waiting inside a working engine. The Merlin's journals and big ends rode in lead-bronze alloy bearings, but the bearing began as a steel shell. Casting tubes were fitted into it, and their edges were spun over on a lathe to lock them in place. The shells were preheated before the alloy was poured from a controlled electric induction furnace. Then the new liners were cooled in a special cylinder, with water jets spraying inward from all around. Among the light alloy parts, the supercharger rotor was the one that left no room for error. In service, it could be driven at between 20,000 and 30,000 revolutions per minute, with its rim moving faster than sound. Perfect balance was not a luxury, it was survival. So the rotor was machined across its whole surface, while countless other Merlin parts went through their own cutting and finishing work. That same discipline ran through the manufacture of thousands of other Merlin components. For each one, Rolls-Royce put thought into the machines and machine tools that would make quantity production possible without letting the old standards slip. Speed was useful only if it still produced a Rolls-Royce part. To police that line, the engineers developed high-precision gauges and complex inspection equipment, going beyond the ordinary gauges used in engineering shops. Inspection did not wait for the end. Each of the 11,000 Merlin components was checked again and again through every stage of manufacture, and then faced a final examination when the work was done. Every factory had at least one air-conditioned, temperature-controlled standards room. There, the gauges used to build Rolls-Royce engines were themselves checked against master gauges and precision comparators, with accuracy on the order of roughly a quarter of a micron. Only after that did finished parts move to subassembly, where the engine finally began to take shape. Assembly was treated with the same order as machining, one planned operation after another. The subassembly benches stood in lines between the finished parts stores and the engine erection lines, so work could flow in one direction. A component passed from worker to worker through dozens of hands. One person fitted a part, another carried out a single operation, and by the end of the line, that component was complete. Larger units, such as the supercharger, were built up on their own, ready to enter the engine as finished assemblies. At the far end of those sub-assembly lines stood the engine assembly shop. Parts and units arrived at the points where they were needed, and the Merlin began with the crankcase. By then, its studs and cylinder holding down bolts had already been fitted on the sub-assembly benches. Down the centre of the assembly line ran a bench-height rail track, so the work could be pushed from one station to the next. At each siding, a turntable let the engine roll off the main track while fitters worked on it. The main line stayed clear, the flow kept moving, and at each stop another component or sub-assembly joined the engine. As it moved down the line, the Merlin turned from a crankcase into an engine. Specialisation governed this shop just as it governed machining. Each task belonged to a crew that did that task again and again, until fitting one particular component became second nature. At the end, an inspector vetted the finished engine, recorded the numbers of its individual components, and gave the whole machine a new number. From that moment, it had an identity. It also received a logbook, ready to carry the record of everything that happened next. First came the test bed. No Merlin was passed for service without running there. For engines bound for the Royal Air Force or the Fleet Air Arm, the Ministry of Aircraft Production required severe trials. Several hours at the rated output, followed by bursts at maximum power. While test engineers watched the instruments and wrote down the engine's behaviour, some Merlins that had passed were still brought back and stripped at once. The run proved that every component could do its job. The strip down asked the harder question: had anything overheated or been overloaded in the process? If the answer was no, Rolls-Royce knew the engine could keep doing that job and still meet the manufacturing standard. Reassembled once more, the Merlins were ready for active service. Yet the work was still not over. On the eve of war, Rolls-Royce faced a problem bigger than raw horsepower. A safe aircraft needed the engine, cowling and fittings designed as one complete power plant, ready to bolt to the fuselage. Rolls-Royce engineers took on that whole package. They made it quickly removable, interchangeable and serviceable at speed. In wartime Britain, that compact idea was hailed as one of the great practical achievements of its aviation industry. And the engines were only part of the story. Once the fighting began, another weakness showed itself. The repair system imagined before the war could not cope with the flow of damaged engines. Rolls-Royce moved fast to close the gap. In 1939, only a few hundred engines were being overhauled. By 1944, the figure had climbed beyond 18,000. Derby became a training hub as well. The Rolls-Royce School of Instruction taught nearly 17,000 people how to operate and maintain the company's engines and other products. The pupils were not just factory hands. They included pilots, flight engineers, and ground crews from the Royal Air Force, the Fleet Air Arm, and the air forces of many allied nations. Rolls-Royce also proved useful far from the airfield. Its engineers developed a small 40mm quick-firing gun for small, fast naval craft, and adapted the Merlin to drive high-speed motorboats. Then came the Meteor, a modified Merlin without supercharging, built to power the first prototype of a new tank. That prototype changed the conversation. The extra power was so marked that Rolls-Royce engineers were pulled into the tank's development, not merely its engine bay. The work led to the Cromwell tank. From the Normandy beachheads to the Rhine, it earned a hard wartime reputation in the advance across Europe. For Rolls-Royce, victory had been built by more than famous designs. Workers, engineers, designers and managers had all carried a share of Britain's burden. With the war over, that same organisation turned back toward the needs of peace. It did not wait long. In October 1945, only 2 months after hostilities ended, a Rolls-Royce jet turbine cut across Britain's skies and claimed a world speed record of about 975 kilometers per hour. The question now shifted. What could that power mean for civil aviation? And what new ideas in propulsion were already taking shape inside Rolls-Royce? Science had not finished with the engine. Rolls-Royce stood ready to turn fresh theory into metal, and to make the latest discoveries work under real load. The next chapter began earlier, in the winter of 1938. A man who freely admitted he had no practical engineering background walked into the crowded, noisy heart of the Derby factory. His name was Stanley Hooker, and the factory around him was anything but academic. Hooker brought degrees in mathematics and physics, plus a deep theoretical grasp of aerodynamics. Given a quiet office beside the roar of production, he turned that knowledge toward the Merlin's troubled induction system. His calculations treated the airflow with a precision the workshop badly needed. From that work came the idea of a two-stage supercharger, forcing dense air into the combustion chambers when the aircraft was operating at extreme altitude. On its first trial, the mathematical solution worked. For the supermarine Spitfire, it meant roughly 113 kilometers per hour more speed and about 3,000 meters more combat ceiling. That helped British pilots climb and maneuver against the formidable Focke-Wulf 190. Hooker then looked beyond the piston engine. He backed Frank Whittle's early jet turbine work, helping steer Rolls-Royce towards the jet power that would break the world speed record soon after the war. When the Britannia needed saving, the answer came from a man who had never followed the usual path into engineering. Across a century of flight, his instincts left their mark, from the huge Olympus engines of the Vulcan bomber to Concorde. In the archives, his career reads like a quiet upheaval, an accidental engineer pushing aviation hard towards the supersonic edge. This is the story of a great aircraft engineer and of the machines he built.